All right, welcome everybody. This is a Flow seminar where Flow stands for Federated Learning One Word Seminar that was created as a global online forum for the dissemination of latest scientific research related to all aspects of federated learning. This includes distributed optimization in general, learning algorithms, privacy, cryptography, personalization, communication compression, systems for federated learning, and many more. So today, it's my great pleasure to welcome our speaker, Mike Rabbat from Meta. So Mike is actually a founding member of the Facebook AI, fundamental AI research team in Montreal. So he holds his bachelor in engineering from University of Illinois at Urbana-Champaign and master from Rice University and PhD in electrical engineering from the University of Wisconsin-Madison. And prior to joining Meta, Mike was a professor at McGill University in the Department of Electrical Computer Engineering, and he in general, he is interested in optimization, distributed algorithms, and signal processing, and he has done a lot of very cool works in federated learning, and today he's going to present one of such on the impact of pre-training and initialization in federated learning. I think we haven't had such talk here yet, and I think we're going to be. It's very nice to have you, Mike. So please go ahead.
Thank you, Samuel. Thank you. Yeah, thanks very much for the nice introduction, and thanks for the invitation. Thanks also for being here to host, given the time where you are. Yeah, I'm really happy to be here to get to tell you about this work today. So Samuel read you the title, and this is joint work with my colleagues John Nguyen, Jianyu Wang, Kshitij Malik, and Maziar Sanjabi. There's a link to the archive preprint there, the most recent version of the archive preprint. And this is the work we'll be talking about today is to appear at iClear a little bit later this year. Right, so as the title suggests, we're going to be talking about kind of the impact of initialization in federated learning. And I guess for this audience, I don't really need to tell you that, federated learning is a really important privacy enhancing technology that makes it possible to do collaborative training of a model among several devices without the data ever leaving those devices, right? And so that gives us ways to provide privacy for the user's data. And kind of the question that we're going to ask, or the motivation for the question we're going to ask in the talk today, is the following. Even though we at the server might not have direct access to client data on devices, in many practical applications of federated learning, it might be possible to get some proxy data. So it's not directly user data, but it might be related to the task that we're trying to train for. And a natural way to use that proxy data might be to pre-train a model to warm start federated learning. And so the question we're trying to get at today, or the thing we're trying to understand, is how would that sort of pre-training impact the training dynamics in the federated setting specifically? So maybe just to set expectations before I jump into the talk too, I want to say that we're going to be approaching this question primarily from an empirical standpoint. So I'll be telling you about experiments that we've run. We don't have as much, I think, understanding from a theoretical perspective quite yet. We'll talk a little bit about it, but I think there's a lot of interesting work. And so hopefully maybe this will be a talk that leaves you with several questions that you're excited to go off and think about and consider afterwards. And as also mentioned to Samuel before, feel free to interrupt with questions at any point. So let's jump in, and maybe to establish kind of common, kind of way of talking about the federated training problem. Let's talk about this FedOpt framework that was introduced in the paper by Reddy and collaborators at iClear in 2021, which kind of is a nice general framework for describing synchronous federated training algorithms. Right, so we have a collection of clients on the left that are going to be participating in training. They're the ones that hold the data. There's a server in the cloud that is going to be coordinating the training. And the server starts with some initial global model. And that's kind of going to be the main thing that we think about today, how that impacts the rest of this training process. So we start with some initialization. And then the way that federated training proceeds in practice, and this is kind of an adaptation of the FedOpt framework, goes as follows. So clients are going to indicate when they are ready to participate to the server. The server is going to use this and keep track of a list of clients that are ready and use that to do some selection of which clients participate in the next round. They form the cohort participating in this round. And the server is going to send its latest model to those clients. Clients are then going to perform some updates locally on their data. And so sometimes in the literature, we'll see that we say clients are going to perform a number of local steps, or actually in practice, it's more common that we will say each client should perform a certain number of local epochs on its local data using some algorithm that generically will be referred to as the client optimizer or client opt algorithm. And the output of this process is a model difference, delta I. And I'm trying to kind of succinctly describe what happens in that little picture on the bottom. I don't know if you can you see my mouse pointer? Yes, great. So if this was the initial model that we received from the server, projecting down to 2 dimensions so that we can see what's happening here, each one of these steps would correspond to one client opt step. And so in this case, maybe we have 5 local batches and we're performing 1 local epoch at this client. And the model difference is just going to be the difference between the point that we end up at after those local steps relative to where we started from, right? So that vector is what becomes the model difference delta I, and that is then going to get sent and aggregated back at the server. And so at the end of this round, the server receives this aggregate client model difference from all the clients that participated, possibly weighted, for example, based on the number of samples that the client had or something along those lines. And the last step to round up this round is, or to finish up this round, is that the server is going to update its global model using some method that we'll generically refer to as server opt. And at that point, now the server has a new latest model. We can repeat this whole process, send it off to new set of clients, they do local updates, aggregate back their model differences, and repeat. Okay, and so each of these corresponds to 1 round in this FedOpt framework. And so again, the question that we're motivating the study today is maybe there's different ways we can think of initializing this global model at the server. We don't necessarily need to start from a random initialization. And so how is that going to impact training dynamics of the rest of this process? And of course, that might depend on some of these design choices that we make in terms of what client optimizer and what server optimizer we're using, among other things. So before we get into the actual study, I think it's also worth pointing out, clearly federated learning is different than just standard distributed optimization problems. And these challenges in federated learning often are summarized as being due to heterogeneity and different sources of heterogeneity. And so one of those sources is data heterogeneity. This comes about because different client devices hold data from different distributions. We don't necessarily assume that all clients are producing data in an IID manner. And so one of the consequences of this when it comes to the training dynamics, and this is something that's I'm sure been discussed many times at this seminar and that has been a major focus of federated learning research, is this notion that when we do local update methods at the clients, these local updates on data from different distributions can cause what's called model drift. And so that means the local optimal for each individual client might not be aligned with the global optimal of across all clients. And that drift might slow down training because essentially we get some destructive interference when we average or aggregate the model updates from different clients. There's also system heterogeneity, which comes about because these different client devices might have very different computing capabilities, might also have different memory capabilities, communications, and so on. And one of the implications of those differences can be that if we limit the amount of time that clients have to perform 1 round of their local updates, it might not always be the case that all clients can perform the same number of updates in that amount of time. It could be either because they have different capabilities, and so some clients just take longer to perform different updates. It could also be due to data imbalance, which is just this idea that different clients might have different amounts of local training data. And so either of these two sources would give rise to clients performing different numbers of local updates, and this can lead to what's called the objective inconsistency problem in a paper by Wang et al. I believe it was at NeurIPS. And so, yeah, these are different forms of heterogeneity that are pretty unique to the federated learning setup and that have been the focus of quite a lot of previous work. And so in this slide, I'm just summarizing some of the previous work in this area. I think there's plenty more, but this is a kind of a representative subsample. Apologies in advance if I didn't catch your method in the slide either, but at a high level, here are some of the approaches that have been proposed in the past to address these various forms of heterogeneity. So FedProx, in the paper of Li et al. 2018, modifies the way that local updates are performed and computed by adding a proximal term that penalizes local updates for drifting too far from the last server model. So it kind of tries to avoid this drift explicitly by introducing a penalty. Other methods like FedAverage-M or federated atom incorporate some sort of momentum or adaptivity at the server, also aimed at overcoming client drift, trying to kind of capture trends over longer periods of time. In methods like scaffold or mime, the training procedure is modified, and we basically introduce control variates, or the server provides some additional state, and for example, a momentum buffer to the client that gets used in those local updates to implicitly discourage drift. In FedNova, this is short for normalized averaging. This approach aims to address this objective inconsistency problem, and it does it by scaling the local step size or the way that updates are aggregated to account for the fact that some clients might perform more updates than others. And other approaches such as FedPD, which is short for primal dual, and FedDyn, which is for, I believe, dynamic regularization, also make some adjustments to the local training objective, essentially, to address this objective inconsistency problem. So it's just a subsample of related work, but to give some idea of different approaches that have been proposed in the past. So, okay, so in this talk, here's what we're going to be thinking about today. The main question is, how does initialization impact federated training? And as I mentioned at the outset, even if the server doesn't have direct access to client data, there might be proxy data that's available in many practical applications of federated training. And so a natural thing to do then is can we somehow leverage that proxy data either during training or at least before training to initialize a pre-trained model rather than starting from a random initialization. And there might be a few consequences of this that we expect. The first one is if you start from a pre-trained model, you might expect that you can converge to a better quality solution in the same number of steps than if you were starting from random initialization, and that's maybe because hopefully you're starting from a better initialization. You might hope also that you converge faster, maybe because you're starting closer, so fewer steps. And maybe one surprising thing that you might not expect, but that we are going to see comes about, at least this was somewhat surprising to us, is that when you start from a pre-trained initialization, seems to be the case that this might diminish the effects of heterogeneity and make federated training behave a bit more like centralized training. Not completely, but a bit more. So this is what we'll be looking at today. Now, I mentioned we're going to be taking an empirical approach. Before I get to that, let me also mention that, of course, we're not the first to have looked into pre-training and how that might, be useful in federated training. And in general, clearly, this paradigm of pre-training followed by fine-tuning for specific tasks is being used pretty widely now, almost ubiquitously in centralized machine and deep learning. And while there isn't necessarily a ton of clear theoretical understanding of what are the consequences of this, there is some evidence that the fine-tuning problem, so when you're starting from from a pre-trained initialization, that might be better behaved or better conditioned than when you're starting from a random initialization. And so the figure on the right is coming from a paper by Mitchell Wurtzman and co-authors called Model Soups. And what this is showing is if I take the weights of a vision transformer, which probably has tens of millions of parameters, and I project those down to two principal components. Theta 0 here is my pre-trained initialization, And the two squares are points that you eventually get to if you do the fine tuning on this task with two different random seeds. And the contours here are showing you the contours of the test error surface projected down to this two-dimensional space. So of course, whenever we go from tens of millions of parameters projecting down to 2 dimensions, we need to be a little bit careful about the conclusions that we draw, but at least what we see in this figure is it seems to suggest that training in this case is much better behaved than, or what we might expect from typical, non-convex deep learning training problems. And in fact, one might even, venture that roughly in this region that we're dealing with, in this case, things look almost convex. Good. And this has also been observed in previous work in the paper by Neshabor that's mentioned here too, Neshabor and colleagues, on what is being transferred in transfer learning. Now, of course, this is not in the federated setting. This is just in the general centralized setup. But to start, this gives us maybe some hope. In the federated setting, there has also been a few studies, mostly coming out in the past year, which focused on demonstrating that when you start from a pre-trained initialization, this closes the accuracy gap. So of course, it's well known, or it's been observed many times in federated training, that when we train a model in a federated way, the quality of the solution that we get to is not quite the same as the quality that we could get to if we were able to get all of the data into one centralized location and not have to deal with all these sources of heterogeneity and non-IID-ness. And so these previous works focused on the fact that federated training closes this accuracy gap, which I think is an interesting one, and which we'll also look at a bit today, but I think we're also going to try to look a bit more at how this impacts other forms of heterogeneity as well. Good. Okay, so we said we're going to be mainly focused on empirical results in the talk today. And so let me tell you about the experiment setup for the experiments that we ran. So we look at 4 different federated data sets. These are mostly pretty common ones in the federated learning literature. So CFAR10, allocated across 100 clients in a non-IAD way using standard Dirichlet allocation approach with alpha equals 0.1. We have the federated version of the MNIST data set, where things are allocated by user, Stack Overflow. Again, in this case, we're doing the next word prediction task with the Stack Overflow data, which naturally is divided into users. And there's also a website, pushshift.io, that has a scrape of Reddit, and we're using a subset of that data set. So the overall Reddit data set, I guess, contains something like 1 million different users. After you filter through the data, we're taking a subset of around 10,000 of those for the purpose of the study today to keep the size a bit more manageable. For most of these models, we're going to look at, for most of the data sets, we're going to look at 2 different models. So for the image data sets, it's a SqueezeNet or a ResNet 18, where batch norm is replaced with group norm. For the next word prediction tasks, language modeling, we have distilled GPT-2 and a simple character level language model. And we're going to want to do some comparison and contrasting between when we randomly initialize these models using the standard approach that one would take to randomly initialize them versus when they've been pre-trained on some related but not quite the same data. And so in this case, for pre-training, we use models which are pretty readily out there that have been pre-trained on ImageNet for the image classification cases. So these model weights can be downloaded directly from the Torch Vision package. For Stack Overflow, when we're using the distilled GPT-2 model, we use a version that was pre-trained on this open web text data. This is available through Hugging Face. And the simple character level language model that we used also for Stack Overflow and for the Reddit datasets were both pre-trained on this Wikitext 103 dataset. Great. So when we're doing pre-training, one thing you'll notice is that in most cases, or in all cases actually, the output domain of the pre-training data is not quite the same as the federated data. So for example, ImageNet has 1,000 classes, but for these federated problems, we care about 10 classes. Which are not necessarily aligned with the ones in ImageNet. Similarly, the vocabularies used in these data sets might not be the same as the ones used in these federated data sets that we're going to train on. And so we do the kind of standard thing in transfer learning, which is just to reset the final linear layer with something that's the right dimensions for the target task downstream, and randomly initialize only that last layer. So essentially, we're transferring the features that were learned from the pre-trained data, and we're going to fully fine-tune that entire model. Okay. Now, in the FedOpt framework, there's a lot of possibilities that we could use also, and we're going to consider, to start, at least a bunch of these different options. So for the client optimizer, we're going to consider, could just have the client do standard stochastic gradient descent updates. It could use proximal updates, akin to what we do in FedProx, where we penalize for drifting too far away from the server model. We could use normalized averaging updates, where we scale the local learning rate and aggregation based on how much data each client has. We could also do the MIME light approach, where the server sends an additional state in the form of a momentum buffer that gets used for local updates. Or we could even just consider having the client take the server model and not do any local updates, but just compute a full batch gradient on its local data set and send that gradient back to the server. Okay. On the other side, on the server side, we're also going to consider three options here. So we're going to consider just standard stochastic gradient descent at the server. And so just, for example, combining SGD at the clients with SGD at the server would be what's typically referred to as federated averaging. We'll also consider having the server use SGD with momentum, right? So SGD plus at the clients plus SGD with momentum at the server would correspond to Fed average M. Or we could have Atom at the server. And again, with clients doing SGD, that would correspond to Fed Atom. And of course, we can consider all these other combinations as well. And we'll take a look at those. Now, in terms of how we're going to do this comparison, every method is going to have the same number of rounds for training. They're going to use the same local batch size and the same cohort size. But of course, there's other hyperparameters that can make a big difference in the performance of these methods, things like the client learning rate, server learning rate, other coefficients like the penalty for the proximal term in a FedProx update. So things like this, we're going to tune specifically for each method and each workload, so each data set and also each initialization, to try to give each method its best shot. Good. Okay. So maybe this is a good place for me to pause in case there's any questions about the setup so far. If not, that's okay.
Yeah, maybe I was just wondering about the previous slide where you use ResNet 18, but you use group norm. Is there a particular reason for that and not to use batch norm?
Oh, yeah. So there's been plenty of discussions in the literature about how batch norm causes some issues for federated training, essentially because your batch norm statistics also capture aspects of your data. And so those previous works I should have referenced in the slide here, but they recommend to replace batch norm with group norm. And so essentially this makes the model a little bit more amenable to federated training. Yeah.
Thank you.
Mm-hmm. Great. Okay, so then let's start to go into the results. So the first question is, does the initialization have any impact on these federated algorithms? And if it does it impact all algorithms equally? And of course, the answer is no. Some are going to behave differently than others. And so to illustrate this, I'm going to show figures like this one, which are kind of messy. So let me take a moment to explain everything that's being shown here. So clearly there's lots of different algorithms that we want to try to compare. Each algorithm corresponds to a different line. So in this figure, to not show too many algorithms at once, I'm only showing 9, which is still plenty. So these 9 algorithms are organized in the following way. So the color tells you what is the server optimizer. So blue corresponds to Fed Atom, red to federated averaging. So just SGD at the server, green to SGD with momentum at the server. And the line style tells you about the client optimizer, proximal, SGD, or MIME light in this case. Okay, now in this figure, there's actually only really 18 data points that we care about, and these are shown at the extreme ends on the left and on the right. And these are the 18 final accuracies kind of the best accuracy is achieved on the test set for each of these different methods. On the left, when we start from a pre-trained initialization, and on the right, when we start from a random initialization. I do want to point out that the axes on the left and the right are not using the same scale, and they don't show the same range. So you should be aware of that. Right? So for example, on the left, in the pre-trained case, we see the range goes from 23 to 25. This is accuracy for next word prediction. Higher is better. On the right, we see the accuracy ranges from 15 to 20. And so this is one thing that we definitely see consistently, which is when you start from a pre-trained model, the difference that you see between methods is smaller compared to when you start from a random initialization. You see a much broader difference there, right? Range of 5 versus a range of 2 on this side. Okay. Then you might be wondering, okay, if there's only really 18 kind of important data points, what's happening with all the stuff in the middle? And there, I guess the point is to say that the values in the middle don't really matter. But the point we're trying to illustrate by showing the data in this way is if you look at these lines, they interpolate the value from the same algorithm in the pre-trained case across to in the random case. And what we see is that these lines cross quite a bit, right? It's spaghetti. It's not that all lines go in parallel across to the other side, or that the ordering remains the same. And so this tells us that depending on which initialization, even if we tune the hyperparameters for each method to try to do its best for each initialization, depending on how we initialize, different methods perform differently, and some might be more preferable than others. So this kind of relative ranking of algorithms changes. Is that part clear? So that's for one data set, but we see these same kind of trends across all of the data sets that we looked at. That the range typically is tighter for the pre-trained initialization, so which algorithm you use might not have as big of an impact, and also that the relative ordering changes quite a bit. And one other thing that we kind of observe consistently across at least these 3 workflows, and to some extent in Feminist too, is mostly blue at the top, right? And that kind of suggests that using federated atom or using atom at the server probably makes a difference, especially if you're starting from a pre-trained initialization. That seems to give consistently among the top performers. And so to simplify some of the things for the rest of the results that I'll be presenting, we'll focus for the most part on federated atom, so atom at the server and SGD at the clients, and in particular that also reduces the number of hyperparameters we have to tune at clients. We only have a learning rate, a local learning rate at the client. Okay, so we see now that there's certain methods that maybe perform better than others, and that the ordering definitely depends on whether you start from a random initialization versus a pre-trained initialization. Those previous plots just showed you the value at the end of training, but we can also look at some representative curves during the course of training. So these are showing you accuracy as a function of rounds. And for the different data sets and models, for a subsample of those, this is specifically for FedAtom. And so a few of the things that we observe in this case are that pre-training clearly is consistently achieving a better final accuracy, right? The blue curves are pre-trained, they're consistently on the top, especially at the end. They may converge faster, right? So for example, in Feminist, we get there quite quickly, similarly in Stack Overflow. And that might be because they start out at a much higher accuracy, but that's not always the case. So for example, in CFAR10, these two are not all that different, but even there we see that the pre-trained model converges both to a better accuracy in the same number of rounds, and it gets up there quite a bit faster than when starting from a random initialization. Good. Something else we see, which is consistent with some of what's been observed in the past, is, or in other work, I should say, is, we can ask this question now, what if there wasn't data heterogeneity? So, for example, in each of these data sets, in the non-IID case, there's a natural partition of the data across the different users. We can just take the data and randomly shuffle it and then reassign points to the users as well. And that essentially makes the distribution across users IID subsamples of the overall training data set. And what we see consistently in this case, and this again is for FedAtom being tuned for each initialization and each setting, FedAtom is less sensitive to data heterogeneity when we start from pre-trained weights. So the difference between non-IID and IID values, sure, there's still some gap, but the gap is smaller pretty consistently. Compared to when we start with the random initialization, this gap is much larger. Something else I think that's interesting and that ties into heterogeneity is that it appears that starting from a pre-trained initialization might allow for running more local epochs without degrading performance, right? So this bar chart here is for, again, running federated Atom on the CFAR10 data set with ResNet 18 with group norm, and looking at what happens as we increase the number of local epochs. And, typically we would expect, because of heterogeneity and data heterogeneity in particular, we would expect there to be more and more client drift as you increase the number of local steps or number of local epochs. And when starting from a random initialization, we do see that at least up to 4, there's this trend that, the accuracy drops. It goes up a little bit when you get to 8. I would imagine if you go further out, it's going to continue dropping again. And we don't see that when we start from a pre-trained initialization. So this also suggests that something about the overall law surface or training dynamics when we're starting from a pre-trained models appears to be very different than when we start from a random initialization. In fact, it turns out local updates may not even be necessary. So if we look in this plot, we're showing for these 2 different data sets, Stack Overflow and CFAR10. In green, you have what happens if you start from a pre-trained initialization and you use Fed Atom with local SGD updates. So Atom at the server and at clients, they're doing local SGD updates. And the blue dotted line, which is not too far off and pretty consistently follows the green line, is what happens if you do Atom at the server and each client just computes a batch gradient without doing any local steps. And so, when you're starting from a pre-trained initialization, there's not much of a gap between these methods. On the other hand, when you start from a random initialization, as is shown in the red and the orange curves here, there is quite a big gap. And so then local updates actually give you quite some benefits. Okay, so next we kind of ask, okay, does the existing theory for convergence of federated training methods maybe help us support or explain any of these observations? Is it consistent? And we're going to see it is to some extent, but not as much as we would like. And I think this maybe opens up some questions for future work here. So just to pull in the standard typical formulation, like we might, in analyses of federated training algorithms like local SGD or Fed average, we might say that we want to minimize some global objective, which is the sum over all of the clients of that client's local objective. So this is the objective of client I, may be weighted by some factor PI, which could be, for example, the proportion of data that's held at client I. And if I paraphrase a typical result in the literature, and this one is coming from a paper of Karimi Reddy et al., I believe this is the scaffold paper, but there are others in the literature that would maybe consider different assumptions or slightly different algorithms, but I think would get us to a similar discussion here. In the non-convex setting, because we are talking about training deep networks, which are definitely not convex, the types of results that we see usually say something like the following. So if we look at the average or the expected norm squared of a gradient at some averaged model after R rounds, right? If we're converging to a stationary point, we're hoping that this is getting small. And this is going to be upper bounded by something on the right-hand side that depends on a few terms. So R is the number of rounds that we've completed of federated training. This would be assuming that every client performs the same number of local updates in that round, and that number of updates is K. M here is the number of clients that are participating in training. F captures the quality of the initialization or the loss at initialization. How far is that initial global loss relative to the best we can hope to achieve for this model and this data? If we had the data centrally also, well, if we treat this as our objective, I should say. And then there's this other term which depends on zeta, and zeta here is related to a gradient dissimilarity bound. It's looking at, so actually there's 2 parameters in this bound, b squared and zeta squared, that we get to choose, but these can be chosen in a way to try to make this, basically on the left-hand side, we have what's the difference between the average norm squared gradient at different clients versus the, in this case, the norm squared of the average gradient, perhaps scaled, right? And so having zeta be smaller would correspond to less dissimilarity, more agreement amongst the gradients at different clients. And so what this kind of a result tells us was clearly if we have a better initialization, F is going to be smaller, and so we might expect to do better. And similarly, if we have less heterogeneity or less dissimilarity, I should say, which we might expect if we have less heterogeneity, then then we might also expect to do better in our training. Now, I do want to pause to point out, when we are changing the initialization, we're not actually changing this problem at all, right? And so we're not actually changing gradient dissimilarity or any notion of heterogeneity, at least the way that the assumptions are stated in the current bounds. Now, it might be possible to adapt to these bounds so that we only care about heterogeneity along the trajectory seen during training, kind of a more localized assumption as opposed to a global assumption. That might be one interesting direction. And then it might turn out to be the case that when you start from a randomized initialization, pre-trained initialization, you can actually show that you're, impacting that kind of a term. But for now, the analysis doesn't let us really say anything that's not tied to the initialization. So the only factor here that's tied to initialization really is F. Great. The other thing we can say, and that's pointed out in several papers that have similar kinds of bounds, is if you want to achieve this asymptotic 1 over square root of rounds times number of local updates rate, which would be akin to what we would expect in a centralized setting, then the number of local steps shouldn't be too large, right? So that number of local steps K should be upper bounded by usually something that depends on the number of rounds, the quality of the initialization, and heterogeneity as well. And so again, this would tell us that if the loss at initialization was lower, then we could take more steps. And so that might help explain some of what we were observing about being able to take more local epochs. So then the question might be, well, do we actually observe that the loss is always lower when we start from a pre-trained initialization? And it turns out it's not always the case. In many examples it is, but not always. And so what I'm showing in the table here is for all the data sets and for the different models that we considered, what is the training loss at initialization when you start from a pre-trained or a random initialization. And so in some cases, you can see that the random initialization is actually lower. In some cases, they're not so different. And in other cases, the random initialization is higher. And this is mostly in the image classification tasks where we see that there can be examples where random initialization is lower, at least in the language modeling tasks that we looked at and for the initializations that we considered. It does seem like pre-training always gives you a better initialization. Now, you might be asking, how is it even possible that a random initialization could be better than this pre-trained initialization, even in these image classification tasks? So recall that when we're doing the transfer, we still have to kind of randomly initialize that last linear layer because we're transferring from a data set that was with a different number of classes and different meanings of classes. And so I would expect that is the explanation for why in some cases that random initialization might be lower. But even if it's lower, what we've seen consistently in all experiments, even if the training loss is lower at initialization, at the conclusion of training, we always get to a better loss when we start from a pre-trained initialization. Good. We can try to probe a little bit deeper and maybe try to get some hunches, at least empirically, of why pre-training might help federated optimization. But this is definitely not grounded in the theory as well as we would like. And so I think this is also maybe room to explore further for future work. One hypothesis might be that pre-training helps align client updates. So when we start from a pre-trained model, even if we do local steps, because the client updates are relatively well aligned, they're not going to drift as much. One way to measure alignment would be to look at sort of an adaptation of the definition of gradient diversity given in this paper by Yin et al. So here we're using the model updates, which aren't exactly gradients, but we'll treat them as kind of pseudo gradients. And what this gradient diversity definition looks at is, sorry, I might have a typo. This is supposed to be the sum of the norm squareds of the individual model updates from each client over the norm squared, so the square should be on the outside, norm squared of the sum, right? And so if all of the client updates were perfectly aligned, pointing in the same direction, then this ratio should be 1. And on the other hand, if they're not perfectly aligned, there might be some, kind of cancellation in some dimensions. And so then this is going to be larger than 1. So the more larger than 1 it is, the more diverse it is, the more diverse these different model updates from different clients are. And so one thing we see pretty clearly, and I believe this is along the trajectory taken by Federated, probably for the CFAR 10 problem, but I think we also observe this pretty consistently across other workloads and other training algorithms as well, is that when you start from pre-trained initialization, gradient diversity is consistently lower throughout training. And so this is telling us that the gradients coming from different clients are not as different as they are in the random initialization case. The other thing we can look at is how consistent are the gradient directions, now the average model update directions we're getting from clients across rounds. And so here what we do is we take the averaged update that the server sees at round T and look at what is the cosine similarity with that same averaged update that the server saw at the previous round. Bearing in mind that we are using client sampling in these experiments, and so these are going to be almost always coming from different subsets of clients. And so what we see in this case is, at least early in training for some initial rounds, it does appear that this cosine similarity is higher when you start from a pre-trained model. And this would seem to suggest that no matter which clients you sample, all clients are going to want to push the model in roughly the same direction over time at the beginning of training. And then you might expect that we get to some sort of rough basin around a local minimum, and then clients might not exactly agree on the direction, or over time, they might not agree also on the direction that the model should be updated. Good. The last thing that we look at, which I believe also might be something to investigate further in the future, is the hypothesis that perhaps when we start from a pre-trained initialization, we're starting from sort of a better conditioned region of the loss landscape or the training landscape. And so to investigate this, we look at the largest Hessian eigenvalue at the initialization. And so again, this is for each data set and for different, for pre-training versus random initialization in this case. And here we consistently see that these largest Hessian eigenvalues, which might be a measure of smoothness, sort of a proxy for Lipschitz constant in that region, it's consistently lower when you start from a pre-trained initialization. So that also seems to point in the direction that pre-training helps make the problem a little bit nicer, more well-behaved. Great. So at this point, I can maybe start to conclude. So I guess the message of the talk today is maybe to think about pre-training, if you can, if you're doing federated training, and that pre-training and starting from a pre-trained initialization or otherwise warm starting your federated training process may help alleviate some of the effects of heterogeneity in federated training. What we saw, and perhaps might be also useful to consider, is that when you are starting from a pre-trained initialization, what seems to matter the most is using an adaptive optimizer at the server, like FedAtom or something along those lines. It seems to matter more than other ways of trying to deal with data heterogeneity by, say, using more complex control variates or modifying the local updates. At least that's what we've observed in these experiments. A recommendation going forward now for the community might be, if you're introducing new methods for federated training, consider evaluating them not just when you start training from a random initialization, but maybe also consider evaluating them when you start from a pre-trained, warm-started model, and compare to other methods in both of those scenarios. Pre-training might be relevant for some cases in practice. Of course, there are limitations here, and so it's not always going to be the case that we have proxy data at the server, so we can't always do this pre-training, but it seems like if you can, it might be a useful thing to do. think there's plenty of directions to extend this work for the future. So we, try to talk about some of the connections to existing theory to better quantify the effects of this initialization and pre-training. But I think there's plenty more work to be done there to both better understand some of the observations that we make in this work from a theoretical perspective, and also to understand things like bias and distribution shift, right? So you might expect that the distribution of the proxy data available at the server might not exactly match that of what is on the clients, and that potentially introduces some bias into the training process. We need to understand either how to mitigate that bias or what are the effects of that bias. And also this is of course related to distribution shift, where you're transferring to a federated task where the distributions are different. So I think there's things to draw on from that literature as well. In this work, we focused on just doing standard supervised pre-training and transfer learning. But of course, there's lots of other forms of pre-training that one might consider as well. Meta-learning can be seen as a form of pre-training if you have the right data and, I guess, information available to do meta-learning. And similarly, self-supervised pre-training might be definitely something worth investigating further in the federated community. So yeah, just to wrap up, I guess there's another link to the paper. And I include my email address at the bottom in case you have questions and want to reach out over email, but I'm also happy to take questions live right now. And thank you again for your attention, and thanks for the invitation, Samuel.
Yeah, so thank you, Mike, for excellent talk. So please, if you have a question, do post them in the chat or just raise your hand. I see there is already a question from Edwin. So let me try to unmute Edwin. Yeah, please go ahead, Edwin. You should be able to unmute yourself. Okay, so so I'll just read out loud the question. So first of all, he's saying thank you very much for your very interesting talk. And the question is, did you investigate anything on how to choose the best pre-trained initialization? For example, something related to task domain similarity between pre-training and client data?
No, it's a great question. I think that ties into some of the future work that should be done here. No, we just focused on this initial question of, if we start from a pre-trained initialization, is that going to significantly change our perspective on federated training dynamics and kind of how we think about different algorithms? So, but we just started with the simplest thing of saying, take pre-trained models from pre-trained on standard data sets that are in the open and out there and easily accessible. That also, part of the motivation was to help it make it easier to reproduce the results in this paper. But I think there's plenty more that can be done to investigate in that direction. So, yeah.
Yes, so he's saying thank you. Then we have one raised hand by Steve. Let me just unmute him. Yeah, please go ahead, Steve.
Right. Hi. Thanks for the great talk and the great insights. Actually, I wanted to ask two questions. The first one is that I see that you start from quite large tasks compared to the downstream tasks. So, for example, you start from ImageNet, and then the downstream task is classification on CIFAR 10, which is quite more simple, I would say. Do you think that if the downstream was much different or less or more complex than the original one, that you would have the same kind of behavior during federated training?
Yeah, I think it's a good question. Also something to follow up on. We did spend some time thinking about which pre-training data sets we wanted to use. For the image ones, we converged on ImageNet because those pre-trained models were readily accessible, but it is indeed quite a big difference in complexity, but also just in the types of images that you see in ImageNet, even in terms of size, right? The images typically in ImageNet would be, downsampled to say 200 and something by 200 and something images, and in CIFAR 10 they're 32 by 32. But I think this generally ties into the previous question about understanding impacts of domain shift, and I would only expect, at least intuitively, right, and from some of the literature that we know on domain and distribution shift, we know that if the pre-training and downstream domains are more similar, then one might hope that things are going to be even better. The situation might be better when starting from a pre-trained model. It doesn't tell us much about the impact on heterogeneity, but at least in terms of initial loss and things like that, it seems natural that it would be the case. I will mention for the language data sets, I think they might be a little bit closer, at least in terms of size and complexity, than the image ones, but no, it's a totally valid point.
Mhm. And then second question, if I may. So can you use a previously federated model in order to act as a pre-trained model for a later task that is downstream? Have you had any experiments with these kind of setups? Where the
So
pre-training itself is not centralized, but it's like, again,
federated
federated.
pre-training.
Mhm.
Yeah, so I know there's other work in the literature that has looked at things like federated self-supervised learning as a form of pre-training. It's not something that we explicitly looked at in this study. I guess you could always look at, I mean, for sure, there's been experiments that have been done in the past where essentially we do a single pass over all of the clients in the data set. Right. And so in that case, you could always say, well, at one round, if I were to call everything that happened before that, my federated pre-training and everything that comes after that, my federated fine-tuning, I guess you can see how that behaves. But that would be a little bit different than what we looked at in this study for sure.
Great. Thanks a lot.
Yeah, thank you.
Yeah, then there's a question by Shang Yang. Let me just unmute him as well.
Hello, I have a question about the pre-train effect. Actually, if we use the extra data, which is close to our task data set, does it makes the training set actually bigger than what if we combine all data together and start for the federated learning? So it seems also will lead to the higher accuracy or the better performance.
Yeah, for sure. It's not surprising that we see better accuracy. One way to think about it might be that we're training on better data or more data, but at least in the case of the experiments that I was talking about today, and as has come up in some of the previous questions as well, the distribution of that data that we pre-trained on is not necessarily the same, and it is almost definitely quite different from the distribution of the data that we were fine-tuning on, doing the federated training on. And so I don't think one can just say that we're getting more data and that necessarily helps for the downstream task, because if the more data, if it's closely related, then I agree with you. And I know you mentioned that in your question, but it's not necessarily obvious or straightforward how to measure similarity of data sets in a very, it's not clear what is the right way to measure that right now, I think.
Yeah, okay, thank you.
Yeah.
Don't see any other questions in the chat for now. So maybe let me ask. We still have a time. Let me ask you. So when you did this theoretical comparison, so you chose the scaffold rate, but I thought that the scaffold rate has a problem that essentially, like, if you wouldn't run local steps, then the second term that so if you, instead of local steps, you would just run here. So instead of like running just local steps, you would just increase your batch size to be k. Then the second term would disappear, and you couldn't actually do any of those, and that would be like strictly better than scaffold. And you couldn't kind of argue about number of local steps that you should take. But I suppose that if you would take this more like a newer results where I think it's kind of typical to show that you can benefit from federation when there is a
Hessian similarity.
Hessian similarity, right? There you actually have the bound that you actually have to run a certain number of local steps, and I suppose that you would come to the same conclusion, but I'm not 100% sure, but I think maybe better way to present this.
That's
You
probably,
see, like,
that's a very good call. Yeah. So, I mean, this result in particular, I should have said, is for Fed average.
Yeah.
The results that you're talking about that benefit from, at least the ones that I'm aware of, including the one in your paper on Fed Shuffle, they benefit from Hessian similarity to get better rates and actually see benefits of local steps. Those also involve some sort of momentum variance reduction. Right?
Yeah, yes. Yes, but you can also use this like kind of momentum variance reduction, which is kind of very resembling to this like global momentum.
That's right. That's right.
Yeah.
And actually that's a good point, because that might help at least partially understand some of this observations that we saw, that having some kind of momentum or adaptivity at the server can make a big difference. Yeah, no, that's a good point. We should go back and look at that. I think it's a good suggestion. Thanks.
Then sometimes that I was also curious about is you were showing this like the way how you do pre-training. So essentially, like you have a model that has different output size. So you actually have to reinitialize the last layer. Would that make sense to actually like to get the lower starting loss to first try to kind of align the last layer with the data set before optimizing the rest that you pre-train?
So if you have some way to do that, then yes, that would have made sense. We wanted to try to keep it as simple as possible, and so we didn't consider doing that. But if you had information about, or some way to map, say, classes or vocabulary.
What I meant is actually to start training with like the thing that you pre-train being frozen, the thing that you actually randomly initialize, like to train it for a few epoch on your actual data set, to kind of first align it and then to train the full data set, whether that would make a difference or not. Yeah,
I see. So I'm not sure I completely follow what you're suggesting, but I think maybe the answer is potentially it could. You still have the issue that the output dimension for your federated task is different than for the input task. So I think you need to do something.
So what I meant is like you finish your pre-training,
right?
Then you reinitialize the last layer to match your federated task. But then you start your federated task by only training the last layer with the.
Oh, I see.
Yes,
I see.
And then like once you kind of
freeze
converge,
the feature extractor and only train the classifier. Got it.
Because it's a convex problem, so you shouldn't have that much of problem like retraining.
That should be pretty quick. Yeah, that would be a reasonable thing to do for sure. So we didn't do exactly that in the paper. In the appendix, one thing we did look at is sort of the first step of that, which is what if you were to only freeze the feature extractor and then train only the classifier after pre-training. And in some cases that does almost as well as doing federated training of the whole model. In other cases, it's not quite, but then like you're saying, maybe you should unfreeze it and do the whole thing afterwards. But no, that makes a lot of sense. And I think that would be a very sensible thing to do. Yeah.
Let me just check whether there's another question. There is none. So maybe just one quick last one. Did you actually train the number of local steps or rounds for clients, or you had it fixed?
For most of the experiments, we had fixed that, I believe, at 1, except for the one where we varied it to see what was happening. Yeah. But I think otherwise we just kept that one fixed at 1. But that could be something else to sweep over, yes.
Yeah. Because I was kind of wondering, especially because of the results that you showed at the beginning, that there was like the mismatch between like that actually like the different model were performing well for randomly initialized and different one for pre-training, that I was wondering whether you kind of observe the effect, because like sometimes that you see kind of that effect, like when you have like two greedy models, they converge fast, but they cannot converge to a very good solution. So that you would expect, and that might be the ones that take many local steps, right? While the ones that are like more precise, they might converge slower, but if they start with very good solution, they might converge to very high precision. So whether you kind of observe that kind of artifact or something like that.
So all methods had the same number of rounds, and we tuned things like the local learning rate and the server learning rate per method and initialization to try to give each method its best chance. But it's it's entirely possible, for sure, if you were to change the number of rounds, you would get different hyperparameter settings that might work better for some methods. Yeah, that part's possible. I do think that the same general trends would hold.
All right. Yeah. Thank you.
Okay.